Hello everyone, my name is Tasneem Safdari and in today's video I am going to discuss the question number 2 of end sem. We have discussed question number 1 both part A and B in previous video which is uploaded on my YouTube under the playlist end sem, so you can look to it for its explanation. So let's start with question number 2. A part, demonstrate an algorithm that uses Bayes' theorem with a small example where prior probabilities and likelihoods are given. So what is Bayes' theorem? So Bayes' theorem is used to compute the posterior probabilities when we have given the hypothesis H and evidence as E. So we are finding the probability when we have a hypothesis which is H and evidence which is E. So P of H upon E is equal to P of E by H into P of H upon P of E. So this is the probability. So this is the formula for finding the posterior probability. So what are the terms? Let's see. So P of H is our prior probability and P of E upon H is our likelihood. So we are given in the question, means we have to take an example where we are given the prior probabilities and the likelihoods. So prior probability is P of H and the likelihood is P of E by H. So and P of H by E is our posterior probability. So what is P of E? So P of E is the total probability of evidence. So in starting we are given the evidence and hypothesis. We have evidence and hypothesis and that is used to find the posterior probability. So P of H is our prior probability. So P of E is our total probabilities of evidence. So this is Bayes' theorem. Now we algorithm using Bayes' theorem. So first we'll define the hypothesis and evidence. So H, hypothesis is email is spam and E is email contains the word offer. So H is our that email is spam and E says that email contains the word offer. So we'll collect the prior probabilities. Let's assume that P of spam is 0.4 and P of not spam is 0.6. Naturally, if it is 0.4, so 1 minus 0.4 is 0.6. Now we'll collect the likelihoods like P of offer upon spam, which is 0.7. P of offer upon not spam is 0.2. So we are given with offer these likelihoods. Now compute the total probability of events, which is P of E. So P of E will be equal to P of E upon spam into P of spam plus P of E upon not spam into P of not spam. So when we'll get P of E, it will be equal to 0. So we're substituting the values. We know that P of E upon spam, everything we are given we have assumed P of spam, P of not spam. We are given P of offer upon spam, P of offer upon not spam. And when we put the values into the particular formula, P of E, which is obtained in 0.40. So this is the total probability of evidence. Now we need to compute the posterior probability using Bayes' theorem. So posterior probability, we have identified the formula for the posterior probability. So it is when we put the values in it, we get the answer as 0.70. So now we'll interpret the results which we have got the answers from it. We'll interpret the results. So it says that if the email contains the word offer, it is if at any point it contains the word offer, the probability for that email to be spam is 70%. Even though what we have assumed, even though it was originally at 40%, but when we have calculated, we got to know that if an email is containing the word spam, it is more likely to have the probability as 70%. So this is the final answer, where prior is 0.4, which is P of spam likelihood, P of offer upon spam, P of E is 0.40, and posterior probability is 0.70. So Bayes theorem updates our belief about whether an email is spam after seeing the evidence. So when we have evidence, if we get updated, our beliefs get updated. So evidence is more important. So this was all about part A of question number 2. Now let's move on to part B, which says that we have to compare binomial, normal, and Poisson distribution. So binomial distribution, we apply it on discrete data sets when we have discrete data with us, and we use it when we have number of successes in n independent trials. So to find the number of successes, so we had we number of heads in 10 coin tosses. So the coin is tossed 10 times, so we need to find the number of heads from it. And we have parameters like n, which is the trials, number of trials, like we have tossed the coin 10 times, so n becomes 10. Now then P, probability of successes. Okay, now mean is n into p. The document contains some error, it is printed 3 times, but mean is n into p, and variance is np 1 minus p. So what is 1 minus p? It is actually the probability of failure. So failure, it is represented by q, and q is equal to 1 minus p. So variance becomes n into p into 1 minus p. Now normal distribution, it is on the continuous data sets, and it is distributed symmetrically around the mean. We have mean, and the data is distributed around it in a symmetrical manner. We have examples as height, weights, test scores, and parameters like mean. We have nu and sigma as standard deviation. So mean is nu only, and variance is sigma square, standard deviation square. Special, it is a bell shaped curve. In normal distribution we get a bell shaped curve. Poisson distribution, it is for the discrete data set, and it is used when number of events, we have a fixed interval like time, distance, area. So it is used for counting number of events in a fixed interval. When we have fixed interval, like example, we have a number of how many calls, or number of calls in a call center in an hour or per hour. So we have a constraint that for 60 minutes or 1 hour we need to calculate the number of calls. So we have an interval with us. Now parameter we have is lambda. So mean is also lambda, and variance is also lambda. Now we have a comparison table. In a tabular form we are making a comparison. So nature, it is of discrete, and normal is continuous, and Poisson is also discrete. Binomial, number of successes in fixed trials. Real valued continuous data, we find the number of successes. Here we have a continuous data with us, and here it is the number of events in fixed interval. Now shape, the shape is varying with p. It is symmetric when p is 0.5, and we have seen normal is bell shaped, and Poisson is skewed. It can be right, left, so it is right skewed. And parameter is n and p, and here it is nu and sigma, and here it is lambda. So mean is n into p, here mean is nu, and here it is lambda. And variance is np into 1 minus p, sigma square, and lambda. Example is heads in 10 tosses, heights of people, and of calls per hour. Here fixed number of trials, when we have a fixed number of trials, and normal when data is continuous, and Poisson rare event counts. And relation approach, now normal. So when we have n large in binomial, so our data approaches, we approach to normal when we have n in large amount, and it approaches and Poisson distribution approaches to normal When we have lambda, which is the mean or variance, it is in large amount, which is in large. Lambda is large, so it approaches to normal. And here in binomial, if n is large, it approaches to normal. Okay, so this was the comparison between binomial, normal and Poisson distribution. So we have discussed question number 2, part A and part B both. I hope you liked it. Thank you so much for watching.